Quantum computers are exciting because they could carry out multiple computations at once. This won't make browsing the internet any faster, but it will, for example, let drug companies test all of the possible outcomes of different chemical combinations at the same time, which could make discovering new drug treatments exponentially faster.
Conventional computers are built from silicon chips that have more than 1 billion miniature transistors etched on them. By cramming on ever more transistors, computers have been getting faster and faster. The problem is we can now squeeze so many components on a chip, we just can't get any more on. We're starting to reach the limits of that technology. Hence, the race to quantum.
Well, so quantum physics is really about the world of the very small. Things don't behave the way that we expect.
For example, an electron can be thought of as a kind of tiny magnet, but a magnet that points to the north and the south at the same time. Harnessing such mind-bending phenomena is what will give quantum computers their speed.
Well, so the quantum computer looks at all possible solutions at the same time and it gives you the right answer. So it works in parallel. So it's that parallelism that you just don't get with classical computer, which really has to go one after the other. So you're expected to get a much greater increase in computational power.
In classical computers, information is stored as strings of zeros and ones. They're called bits, and they're represented on the chip as tiny switches that are either off or on. But the switch equivalents in a quantum computer can be in two different states at once, on and off at the same time. They're called qubits.
The quantum mechanical states of elementary particles, like transistor voltages, can be described in zeros and ones. Depending on the method used, we can apply various kinds of particles to the calculations. Here, the state described by the zeros and the ones is the internal angular momentum of the particle known as its spin. Although it's not possible to describe this particular feature through the use of classical mechanics, it can be likened to a magnetic bar capable of deviations. When the bar is pointed up, the state can be described by a value of 1. However, when it is pointing down, it can be described by the value of 0. In other words, spin up corresponds to the turned on switch, and spin down corresponds to the turned off switch. Using this analogy, we can describe the defined quantum states with the use of binary system, much like a classic computer. However, beyond this point, all similarity ends.
Remarkably, first-generation quantum computers have started to appear. Indeed, earlier this year, Google bought one. The D-Wave 2. The D-Wave uses electrical circuits with superconducting currents running through them, which produce magnetic fields. The circuits behave like magnets and interact with each other.
Finding the minimum energy state of a lot of interacting quantum magnets, the mathematical structure of that is very similar to a lot of really hard problems. We've said, let's build a physical system that finds the answer to a problem physically. It's not changing the problem into a bunch of mathematical equations and solving it with digital logic. It literally is asking, what's the best arrangement of these spins, these interacting spins? It just evolves to that arrangement if we do it right.
Remember that quantum strangeness below 2 Kelvin? Inside this giant refrigerator, Rose's team keeps a few atoms 100 times colder, all to harness those weird abilities to make a new kind of computer.
So let me get this straight. This entire company, this entire building, this entire meat locker, this entire $1 million apparatus is all designed just to make that tiny chip cold?
Yes.
What does the cold have to do with the computing?
In quantum mechanics, the properties that we're trying to harness are very easily washed out by the movement of the atoms in the processor. As you go down the plates through 4 Kelvin, 0.7, 0.1, at each stage we want to remove the wiggling of the atoms so that they just calm down, take a seat on the couch, relax, and when they do that, these wonderful, powerful, magical properties that exist in quantum mechanics blossom out. In quantum mechanics, there's this concept that a thing can exist in two states which are mutually exclusive at the same time, quote unquote. And I'm using those words because the English language was developed before we had concepts to describe what these things actually are doing. But I'm going to give you a roundabout way of understanding this. Imagine that there really are parallel universes out there, and now imagine you have two that are exactly identical in every respect, all the way out to the horizon as far as we can see, down to the last little atomic detail of every single thing, with only one difference. And that's the value of a little thing called a qubit on this chip, which is a contraction of quantum bit. And that qubit is very much like a bit or a transistor in a conventional computer. It has two distinct physical states, which we call 0 and 1 for bit. In a conventional computer, these are mutually exclusive. That device is either one or the other, and never anything else. In a quantum computer, that device can be in this strange situation where these two parallel universes have a nexus, a point in space where they overlap. And when you increase the number of these devices, every time you add one of these qubits, you double the number of these parallel universes that you have access to, until such time when you get to a chip like this, which is about 500 of these bits, you have something like 2 to the 500th power of these guys living in that chip.
D-Wave's fast and furious approach has meant they've actually got a saleable prototype out there. The drawback is its limited application.
It's not a general purpose quantum computer. It's application specific. If you're trying to minimize the risk of some financial portfolio, right, the mathematics is similar. If FedEx wants to find out of all the possible ways we could route our trucks, how do you do it to minimize fuel consumption? Those are all find the best of a vast number of possible solutions.
These are all examples of optimization problems. But of course, there are many other types of problems out there too. So, the race to build a universal quantum computer is still very much on. Research teams here at the University of New South Wales are working on a quantum computer based around a silicon chip with a single phosphorus atom embedded in it. A single electron from that atom serves as the qubit. A very impressive looking machine.
Yeah, so it's basically a scanning tunneling microscope. It's a piece of stainless steel with all the air sucked out from inside, so it's an ultra-high vacuum.
This machine is used to position the phosphorus atom in the silicon chip. But first, a single layer of hydrogen atoms must be added to the surface of the silicon. Then the microscope tip comes down. So you're going to physically knock off individual atoms with that tip?
Yeah, that's great. So that tip will literally, we use it to image the atoms, see where they are, and then we'll apply a pulse above each hydrogen atom and knock it off.
Yeah, it's
and
amazing.
Literally open up a hole of exactly 6 atoms to let that phosphorus in.
This is a world first.
We're the only group in the world that can do it, so it's really, atomic kind of precision to get it in there. And we find that, it never behaves the way we expect. And so you have that beautiful sense of trying to understand right at the atomic level what's really happening.
One of the problems that can be solved is a math problem that we believe to be hard, which is to say factoring really large numbers. And because we believe that problem to be really hard, we have used that as the lock in all of the computer security that we use in the world today, almost all of it. And if that lock can be broken, because the quantum computer makes easy what everyone else believes to be incredibly hard, the person with the quantum computer could break most of the cryptography, all the traffic you see going across the web, a lot of the financial transaction traffic, a lot of the authentication, all of that stuff becomes vulnerable to a computer that's done that. Now, Edward Snowden has told us that the NSA does indeed have a research project to build this, and I actually feel good about that because Snowden didn't tell us they already had one. Now, the way you'll know that someone has a quantum computer like this, if it's made public, is you'll look out your window on Wall Street, and if you see bankers and stock people running, screaming in terror, waving their arms, you know that someone has developed a quantum computer. There are a few other things that could cause that.
So right now we have all this big complex data. People want to make systems that in an autonomous way can do image recognition, speech recognition, machine autonomy. If I have a little robot running around Mars making its own autonomous decisions or autonomous cars. And we'd also like to look at data and make discoveries and see patterns that no human ever would, because we have intuitions for something like faces, but we don't have intuitions for complex genomic data and what it means. So everybody's trying to get insight out of big data. One way that they do that is they build these complex neural nets. So people are now building either abstractions of human neural nets or actual hardware. You hear about neuromorphics. And they build systems where you have these little dots are like neurons in your brain. Those interconnections are like the synapses. And the question is, we don't know how to program something to understand speech. We don't know how your brain does that. What we do know how to do is how to have that network learn from examples and change its own structure until it becomes the kind of thing that can understand speech. But the learning algorithms to find out of all the possible combinations of how to turn the knobs on all those interconnections are horrendous. And as you make larger and larger neural nets, the number of calculations explodes exponentially. So again, if you could search through a large search space of possible interconnections to optimize those neural nets, you can enable a lot of AI that people are looking at now and get more meaning out of large data sets.
You put together a bunch of molecules in the neurons in the brain, a billion of them, 100 billion of them, connect them up in the right way, and suddenly somehow you get this phenomenon of conscious experience. It feels like something from the inside. A totally surprising thing that you can never predict just from the organization of the neurons alone.
You take some person's real brain who knows how to do things, and you scan that brain in fine detail, exactly which kind of cell is where and what kind of chemical concentrations are there. When you've got enough good models of how each cell works and you've got a scan of an entire brain, then you could be ready to make an emulation of the entire brain.